Before Laura's session, there is going to be a dinner tonight at Tula's on Easton Avenue. Immediately after David's talk, there will be a wine reception here. And then around 6:30, Mike will lead a contingent of people over to Tula's for dinner. Speakers covered. There may be some room to cover non-speakers depending on how many of you show up, but all are invited to join.
Our next speaker is Dr. Laura Ruetche. Actually, I forgot to ask you how to pronounce your name. You introduced yourself as Laura, so Dr. Ruetche? Ruetche. Oh my gosh, I'm glad I asked right now. So Dr. Ruetche is a philosopher of physics and science at the University of Michigan. And her interests include quantum field theory. She's written a book interpreting quantum theories, which draws a lot of lessons from quantum field theory, and the relationship between gender and the epistemology of science. So I'm not sure actually what she's going to talk about now, but I'm interested in finding out.
As am I. So I made this slide before I saw the schedule. I left it. I'm also going to start with an apology, but an apology in the sense that Plato's apology is an apology. I'm going to speak out in my own defense. I'm going to tell you where I'm coming from and where I want to go, how I'm going to try to get there, how I'm going to try to get there. So some disclosures about me. I was raised by logical empiricists. And on account of this, my heart believes metaphysics, at least the kind of metaphysics that's informed and constrained by science. If there's other kinds of metaphysical questions, even here, some of them come up, the nature of a binding relation, for instance. I believe that metaphysics, insofar as it's constrained and informed by science, is just methodology. And what I mean by that is something like the frameworks called the metaphysical we choose reflect the aims we have for them, and their capacity to promote those aims is the only scientifically relevant values for choice. It's not just autobiographical still. Because of the sorts of theories I like to think about when I think about theories, I have a suspicion of the idea that I'm labeling naturalism, that there's scientific grounds for choosing any single best unifying metaphysics, and a correlate affinity for a counterposition that is an homage to Arthur Fine I'm calling local veracity. I'll talk more about soon. That the metaphysics of modern science, framing commitments that promote its aims, is various and helpfully so. That's where I'm going to try to get us. Some more facts about me. Reinforcing these kind of suspicions and affinities, an appreciation that the scientific image is still under construction. We're still working on it. An appreciation of the non-trivial role project of interpretation plays in constituting the scientific image. Sometimes as a third of the science itself. Attention to what I think are a significant family of theories that I gather under the umbrella of QM infinity. They include quantum field theories, they include the thermodynamic limit of quantum physical mechanics. Theories that bear interpreting, but whose pointfulness would be blunted by equipping them with a single uniform interpretation. Carry on the image of the scientific metaphor by immersing them in a metaphysics that best develops purportedly their scientific image. Okay, so here's the game plan. I want to distinguish the position I'm calling naturalist from the logo one, paying attention to the ways the project of interpretation and informs each of those positions. I want to champion, that's too strong, gesture approvingly toward a methodological commitment that in the arena of interpretation gives the locavore position, the contrast, what a fighting chance for survival, leaves room. Gives the naturalist position a fighting chance to establish itself, but leaves room for the alternate position, the locavore, to operate. And I want to, this will be the main part of the talk, really draw from these theories I like to think about considerations in favor of the locavore position. Okay, so naturalism. I'm going to sort of flesh it out by quoting from people in the room. Whatever else you might mean by it. What I mean by it is this way of situating metaphysics with respect to physics. We have all the thesis that we have no better guide to metaphysics than the practice of science. And then Ross say of the radically naturalistic metaphysics, everything must go. The French, the raison d'etre of a useful metaphysics is to show how the separately developed and justified pieces of science at a given time can be fitted together to compose a unified worldview. More from later on, one metaphysical proposal should refer to another to the extent that the first unifies more current science in a more enlightened way. Metaphysics should refer to the articulation of unified worldviews derived from the details of scientific research. There's science we now have, metaphysics, the naturalist position is one way to think of metaphysics. It's the best way of making sense of science we now have as a whole. The other way that I'm calling, I'm not claiming it's the only other way, but another way of thinking about things, calling local veracity is inspired by Arthur Fine's The Shaky Game, a book I loved so much in graduate school. I had him autograph it, and he came to the talk. My other autographed books are How the Laws of Physics Lie in World Enough in Space-Time. So, in The Shaky Game, notoriously, Fine articulates a stance on the realism debate, an infuriating stance. It's called the natural ontological attitude. Toward the reading of Fine that inspires the locavore approach, I want to talk about, I'm going to start with a standard criticism of the natural ontological attitude of Noah. I'm going to also notoriously, when Fine presents the natural ontological attitude, it's sort of slogan forward, it's California natural, no additives please. I'm going to work my way towards a locavore reading of Noah by updating the food metaphor. So California natural was there in the 80s, locavores were 21st century, and having crafted the locavore reading of Noah, I'm going to present locavorism, I'm calling locavorism as an alternative to naturalism and also to realism. So setting up a standard criticism of the natural ontological attitude. This is what Fine tells us about the natural ontological attitude sort of amounts to both realism and anti-realism. Commit this discretionary, ill-judged extra step, extra commitment. So what they have in common, they have a core position in common, and the core position consists in accepting the certified results of science not hard or homely and familiar supporting claims, accepting them as true. The mistake they both made is adding something on that distinguishes them as the nature of the mistake they make. By contrast, his position, his stance, the natural ontological attitude, like if they're playing the game with Twister with realist and anti-realist, it's standing aside, like I gotta do that. His position, as he advocates, is just accept the core position. Don't add anything on. Take the ill-judged additional step. So the attractive alternative is the core position and all by itself. This is the natural ontological attitude. Adopts, Fine says, a no theory attitude towards the concept of truth. California natural, no edits. That's the picture. The standard criticism, and here's my juvenile marginalia. So what is the anti-realist add? Some sort of deflationary, instrumentalizing, pragmatizing account of truth. What, though, does the realist add as a core position? A realist, under criticism by Fine, might feel like all I'm doing is accepting as true the certified results of science, taking them on a par with more homely truths like there's tables and chairs. That's just what realism is. So when Fine is pressed to say what exactly it is the realist adds on its core position, he says things like, they thump the table and say realism. And some realists are mild-mannered. Some realists aren't table thumpers. You don't need to be a table thumper to be a realist. So the kind of standard criticism of Noah is, it just is realism. Accepting is true under an theory of truth is all you need to do to be a realist. Maybe there's other ways to be a realist, but that's it. That's the criticism toward deflecting it, and the deflection is going to hold the key to what I'm calling local veracity. Here's a bunch of more Fine dicta about Noah. I'll let you read them. So, drift is Noah thinks it's fine to try to make sense of science, but Noah thinks the unit you should be ingesting when you're trying to make sense of science is local. It's a scientific practice, a particular theory, a particular success, try to make sense of that. Noah opposes the idea that there's going to be some global account. This isn't the end philosophy, you're still trying to make sense, but Rutgers University what it stands for. It stands against generality. It asks how much universality is actually required for understanding. So you're supposed to read these quotations and think, the natural ontological attitude is opposed to global additive, but you're supposed to ask. Is it against them because they're additive? This is the California natural complaint. Or is it against them because they're global? This is the locavores complaint. These aren't exclusive, necessarily, complaints, but they're distinguishable. And I'm going to say, no pretty clearly exercises both, but what helps deflect the standard criticism, I think, make the natural ontological attitude a more interesting position than it's often taken to be, is seeing both that and why the locavores complaint is more fundamental. So here's a dramatization. Remember, what I'm trying to do is show that there is a difference between fine position as I need it and realism. To dramatize the difference, I'm imagining realist in dialogue with the locavore. And this slide is like the middle third of James's preliminary remarks yesterday. It's just this kind of pointy made. Here's the most powerful argument for scientific realism that almost everybody experiences as having immense intuitive pull, called the miracles argument. Theory T, boy oh boy, successful predicts and explains and enables to engineer an iPod that helps us evaluate other scientific theories as a platform for development of further scientific theories unified. The hat pajamas. The best way to make sense of the panoply of successes is to imagine T is true. So therefore, it's a ampliative inference as we follow deductively, but more likely that T is true. The idea. The official, most prominent central official criticism of this argument in the natural ontological in the shaky game is that it's question begging and risky. Obviously, it's risky, it's ampliative, but it's question begging because something like only people who are the realists accepting abduction, blankers, abduction to truth or additives we don't need to insert into our scientific world picture to get along and make sense of it. What I want to do on behalf of the locavore is just bracket those sorts of questions. Bracket for now the question of abduction. And for now, it's accepted the working hypothesis, the realist and Fine, the Noah, the locavore, have the same account of truth. Take that away as the difference between realism and the natural ontological attitude. There's a question that the locavore is still going to ask. It's not going to be stopped from asking by these concessions to the realist. What are we talking about? What is this T? That's the question. And the dialogue goes on in a tone of appeasement. It's a mild manner realist. Remember, the realist says, okay, let's see quantum mechanics. In a way, it's a move in the realist's favor, because when you instantiate the miracles argument of QM taking the place of schematic T, the first premise is on the firmest possible footing. There's no more successful theory in the history of science than quantum mechanics. But the problem for the realist is when she gets to the conclusion, she's got to believe it. She's got to do something that counts as believing quantum mechanics. James already did this for me. What do we believe when we believe a scientific theory? Here's an answer. We believe an interpretation of the theory. Van Frossen's application of that is an account of how the world could possibly be the way the theory says it is, or I think the possibility is adding an important dimension. To say the theory is true is to say the actual world is among its models, but understanding the content of that assertion involves seeing what kind of laws organize the models, what kind of properties we invoke and differentiate in the models, things like that. So the possibility, locating the theory, it's locating the world in the possibility space allowed by the theory is part of what we need to do to understand what you're saying in the theory is true. That's the picture. That's at least I liked. So what we believe when we believe a theory, we believe that it's true. We believe an interpretation of that theory. And now, what James says, this is the realist problem. Execute the conclusion of the miracles argument once it's instantiated using the best possible theory from her point of view for instantiating it. She's got to believe quantum mechanics is true. But how does she do that? With sociological observation, many realists of my acquaintance have something like James' attitude. They don't want to believe quantum mechanics under a realist interpretation. Those who do, depends on where you are, which realist interpretation you want to adopt, and sociological observation. Many realists of my acquaintance just balk. They don't want to do what they need to do to execute the conclusion of the miracle argument. And the locavore says, this is really pretty scandalous. We started with, when presented schematically, seemed like the most intuitively compelling argument there is for scientific realism. We instantiate it with respect to a concrete scientific theory. The instantiation is most beneficial for the realist, and we came up with the conclusion most realists can't bring themselves to board. Some can, but most can't. It seems like something has gone wrong. Here's some lovable diagnoses of what might have gone wrong. So one possibility is explanation of why the miracle argument kind of goes off the rails when we schematize it of QM in the place of T, is that the virtues constituting the success of the theory T, when they're considered like a lofty abstraction, they seem obviously truth-inducive. But when you concretize the argument, look at particular theories, look at the terms of success of particular theories, those virtues might start to seem less truth-inducive. But the terms of actual scientific success would be more opportunistic and honorable than the terms of scientific success abstractly considered. Another thing that might have gone wrong when we tried to deschematize the miracle argument and landed the realist at the conclusion she couldn't bring herself to believe, it might be that what's happening is there's no single interpretation of the theory at issue in a deschematized miracle argument, under which all the virtues, all the successes cited in the first premise of the miracle argument accrue to it. So that's sort of more the weight is sort of distributed across order of different and possibly competing interpretations. In a way, this way of looking at it, the deschematized miracle argument commits a fallacy in many terms. What you're believing when you're believing T has to shift around. And this erodes the support of the virtue cited in the first premise of the miracle argument for belief in the theory T. Let's pick up on the second point, and some sad members of my department have to teach introductory logic to 250 guys wearing backwards baseball caps. And when I read about these slides, I was in the throes of doing that. I couldn't help but kind of see the ground in terms of an operator ordering distinction. Here's the so let X range over the scientific successes of many very credited to the theory T. The isms, realism, anti-realism, naturalism, they aspire to make sense of T or T's success. The realist wants to find an interpretation that would, how the world could possibly be able to explain why T succeeds as well as it does. The fact that this interpretation does this explanatory work is reason to believe in T under this interpretation. Let I range over possible interpretations of T. Here's the big operator ordering distinction. It seems like the realist, and maybe also the naturalist, is banking on something like there's some interpretation such that for all these successes, or for enough of these successes, that's a tricky sort of slide there, for enough of these successes, that interpretation makes sense of that success. The locavore suspects that even for each success, there's some interpretation that makes sense of that success is too much to hope for. So the methodological commitment to take success-making projects in local bite-sized chunks comes along with an appreciation that sometimes it might not manage to make sense, and it comes along with an allowance that sometimes the interpretations by which you make sense in different situations are different from one another. But this is, in fact, being emphatic that there's still room for philosophy on Noah's Ark. The suspicion that the interpretation that makes sense of a theory's success could change from theoretical success to theoretical success. It's consistent with valuing local projects and making sense. There's still work for the philosopher to do. It's interesting work. It's work that amplifies our understanding of science, what it is for science to succeed, and it does. And here, I don't think the slides are as clear on this as they should be. I want to sort of, in another distinction, I want to distinguish sort of methodological commitment to take on projects of interpretation in bite-sized chunks, local bits, particular successes of concrete theories, that methodological commitment. From the hypothesis, which is an additional hypothesis, that when you do that, it might not turn out to be the case, you get the same interpretation that succeeds across the realm of achievement of theory. So, remember the standard criticism of Noah, it's just realism. All realists do is accept theories on their own terms, not part of more homely truths. I think having just drawn this distinction, I can say on behalf of Noah, give a reading of Noah, even accepting that Noah and the realists agree on what the truth is, you can still draw what I'm going to call a cyclops distinction between the local veracious Noah and the realist. And the cyclops distinction is the realist thinks there's one eye. That makes sense of all interpretations. That's not all methods. The local veracious Noah denies this hypothesis to engage in different projects of making sense. He might find different interpretations are needed, possibly incompatible interpretations to accomplish the project of making sense. So whatever accepting the single eye that the realist is after, or not also the naturalist is after, whatever accepting it amounts to, whatever true means, there's just going to be a distinction between the locavore version of Noah and Fine about whether there's such an eye. Here's a related way to make the same distinction. Fine also says about Noah that it's a pro attitude. And this is wonderfully ambiguous. There are two things you might mean when you say something is a pro attitude or a pro attitude towards science. Is it a pro attitude in the sense that it's for science, like Superman is for truth, justice, and the American way? That's one possibility. Another possibility, again, not exclusive. Is it a pro attitude in the way a pronoun is a pronoun and a pro seminar is a pro seminar, in the sense that what it stands for, its content, varies with its context of deployment? If the second thing is part of what Fine means, I think it is, the locavore reading a Fine, it is. There's a follow-up question that circumscribes a certain sort of making sense project. The follow-up question is, if the content of the attitude, that's the natural ontological attitude, varies with the bits of science you're striking it with respect to, how do we understand circumscribe the context that know what content? So I just said both the question of what are the relevant contexts and what content emerges from them. Those are important, interpretive, interesting questions. And this is another way to see kind of the same contrast between the local version of Noah and realist / naturalist. So here's the distinction again, the contrast eliciting question is, with respect to what context do we fit the content of our pro attitude towards science? What we believe when we toe the homely line. Here are a couple options. For Richard Boyd, I think the context is the juggernaut of mature sciences and its sprawling entirety. For Fine, pretty clearly, the character I'm calling the locavore, the context is local bits of ongoing scientific practice applying this theory for this purpose in this way, the same theory for this other purpose in this other way. With different context-fixing strategies, continence is appropriate to different contexts. And also continence is the possibility that maybe there's some context where no content-fixing strategy is appropriate at all. I'm imagining the character I'm calling the naturalist siding with Boyd here against the locavore. So what I've tried to do is kind of defend Noah against this criticism, which just is realism. I said, look what's really going on. Noah isn't about veracity. It's not about how to think about truth. It's about voracity. It's about what size bites you're supposed to be taking when you're trying to make sense of science. I've shown there's a distinction between realism and Noah to be drawn. Noah is offering the hypothesis, the locavore hypothesis. There's no single interpretation that makes sense of all of science. It seems like the realist, in order for the success of science to lend objective support to belief in science, needs such an interpretation to be there. Interpretation of belief which is warranted objectively by the track record of success of science. It's a contrast between the locavore and realist / naturalist, the cyclops hypothesis. There is one eye. And what I want to do next, and this is like the real part of the talk, this is kind of part of what I was supposed to do when I said I'd come, is use these theories I like to think about, quantum field theories and so on, to assess the cyclops hope common to realism, and naturalism. So now things get ugly. I'm going to tell you where quantum theories come from, some of them, not all of them. And I'm going to start by giving you a picture of the structure, the title of the conference, structures characteristic of quantum theories and classical theory. So let's start. Classical theory is a very simple classical theory of particle mass m, moving in one dimension. So the classical state of such a system is a point in a two-dimensional phase space coordinated by observables position and momentum. These observables, these physical magnitudes, they're not the only physical magnitudes that pertain to the system, but other ones, for instance, energy, are definable as functions of position and momentum. That means once you assign a particle state a point in phase space, you've determined with certainty the values, all physical magnitudes pertaining to it has, because they're all dependent functions of its position momentum field. I think it's really important, and here's another gratuitous quotation of Plato. I think it's really important to understanding what physical theories are. They say the world is like to understand that a physical theory isn't just a pile of magnitudes. The physical theory approaches the world and does so by structuring the magnitude it takes to apply to the world. And there's lots of ways you can think about what the structure of magnitudes offered by physical theory are. But a really good way is for the classical theory is the structural picture offered by something called the Poisson bracket. It tells you a little bit about the algebraic structure of the collection of classical magnitudes. Plato's anticipation of inferential role semantics of a sophist, all discourse owes its existence to the reading of forms. So part of what makes physics physics, part of what makes a physical property what property is, the magnitude is the kind of algebraic relationship it stands into to other physical magnitudes. Where algebraic doesn't mean anything. It's just a structure where there's ways of taking linear combinations and products and balancing it. Okay, so that's a picture of the structure characteristic of classical theory, a picture drawn by talking about a very simple classical theory. Structure characteristic of kinds of quantum theories philosophers are used to talking about is something like this. You got a kind of vector space called a Hilbert space, and a state of a quantum system, pure state, other states that are more general that we can define in terms of pure states, is a vector in a Hilbert space. And a lot of what we register as quantum weirdness comes from the structures by which quantum theory represents physical magnitude for observables. The physical magnitude, also known as observables, correspond to self-adjoint Hilbert space operators. Some of the upshots, usually the possible values are quantized. It follows just the quantum mechanics is put together. For each physical magnitude or observable, the Hilbert space operators were party caps, and everybody can play the observable and the operator. For each observable, systems of quantum state determine the probability distribution of its possible values. Usually these probabilities are different from 0 and 1. Also, usually, you've got a system in a state, you've got a pair of observables. There's a trade-off between how well that state predicts the probability, it predicts the value of one of those observables, and how well it predicts the value of the other observables, is the core of the Heisenberg-Minkowski relation. And this kind of trade-off is reflected in an algebraic structure the set of observables a quantum theory traffics in has, where the algebraic structure is captured by what's known as the commutative bracket. So here's a way I'm trying to get you to think about theories. Part of what makes theories the theories they are, part of what makes the magnitudes they work with, the magnitudes they are, is the interweaving of functional relationships that magnitudes stand to one another in. And classical theory is an expression of this interweaving structure, the Poisson bracket relation between observables. In quantum theory, an expression of this algebraic structure is the commutative bracket relation between observables. And this sort of picture sets up a recipe that accounts for where some quantum theories come from. So some quantum theories come to us this way. We've got a classical theory, we love it. We quantize. We follow a recipe that, starting from the classical theory, eventuates in a quantum theory. The quantization of the classical theory. So quantum field theories often arise as quantization of classical field theories. And the recipe we follow is something called a Hamiltonian quantization recipe, and it starts this way. The classical theory you set out to quantize, its observables have a characteristic relation provided by the Poisson bracket. What it takes to quantize that theory is to copy down that characteristic relation to the kinds of observables characteristic of quantum theories. That it consists in copying down the Poisson bracket relation and canonical commutation relations. Got a classical theory, here it's Poisson brackets between its canonical observables. To quantize this classical theory, your assignment is run off, find a Hilbert space, find operators acting on that Hilbert space such that the commutation relation between those Hilbert space operators mirror the Poisson bracket relations between their counterpart ancestor operators in the classical theory. and you're on your way to executing the Hamiltonian quantization recipe to build a quantum theory. There's lots of other ways to get quantum theories. Some of them you just posit the constitutive commutation or anti-commutation relations ab initio. But the picture I want you to have is this is your starting point for building a quantum theory, a set of commutation relations. If you follow the Hamiltonian quantization recipe, they're determined by the classical theory you're quantizing. That's the wrong. So to review, you want to build a quantum theory, set up by build more observables by taking linear combinations. So, here I am building an energy observable with a kinetic energy term and a potential configuration-dependent potential term. It's just another operator acting on the Hilbert space generated by a linear combination of the canonical operators. And this, in fact, is very subtle. Don't stop there. You want to throw in limit points. So if you're in a position where you get a bunch of guys in your algebra of observables as linear combinations and they converge to a limit, you should throw in that limit point too. That guy deserves to be in too. What's subtle is what counts as a limit. I won't get back to that in the talk. I might in the questions. What you wind up with, we've represented the canonical relations that, oh good, these are my canonical observables, taken linear combinations, added limit points, is what's known as the observable algebra of your quantum theory, that symbol, the set of bounded operators, and the Hilbert space there as a representation of your canonical relations. Oh yeah, you probably also want to add states to the physical system and some account of how things change over time. So, again, the story so far, a classical theory of Poisson's rank, that's the germ of the quantization goal, a set of canonical commutation relations. You find a representation of those relations on a Hilbert space. You build up from there, and you wind up with a collection of bounded operators on that Hilbert space. And the usual way of thinking about how a quantum theory comprehends the world, what possibilities it recognizes, how its possibilities of structure, is to say the self-adjoint operators and this collection of bounded operators in the algebra you built, they correspond to observables, and making some innocuous assumptions about what a quantum state is. You're going to think of it as an assignment of an expectation value, kind of probabilistic average, weighted average, to each observable. Given an innocuous assumption of what a state is, pure states in theory, they correspond to vectors, normed vectors in this vector space. Density operators, you know what those are, comprehend all states. Point, details on that, point is starting with a classical theory and following the Hamiltonian quantization recipe. Eventually, with a quantum theory understood as a sort of physical enterprise, where the physical magnitudes reside in a set of bounded operators and the states reside in a collection of things that assign expectation values in the same way to the self-adjoint elements of that set. The set of states gives the possibility the theory recognizes. The observable algebra tells us how these possibilities are structured, what magnitudes pertain to them, and how those magnitudes are organized. So this is the core of an interpretation of quantum theory. Right? There's many more questions we'd like to ask about a quantum theory, but this is sort of an interpretive core account of the possibilities the theory recognizes. Okay, now I'm going to try to make you worried. Suppose I bring in classical theory and I say, over the coffee break, quantize this, and you all come back with your quantizations. You start looking at them and they all look different. So the worry is, might it be that, in fact, this quantization recipe is no good because it can turn out too many ways. It doesn't provide us a route to something that's the quantization of classical theory. Could it be, this is Monique's worry, all your work will be wasted because there's just too many ways to get that quantum theory. Put the question this way. Can we, starting from the same classical theory and competently following the Hamiltonian quantization recipe, can we wind up with different quantum theories? So here's Heisenberg and Schrödinger worrying about that. The standard answer that sort of follows from a theorem articulated, I think, in 1930 by Stone and proven eventually by Neumann, is roughly, if the theory you're setting out to quantize concerns finite and many systems moving in a finite dimensional space, then the resulting quantization is essentially unique. David comes up with a quantization, and Janan does. They might look different, but they're going to stand to one another in a relation called unitary equivalence, where unitary equivalence, I won't go into what it is unless you tell me to, but the importance of it is it sets up the correspondence, sort of correspondence between the states David recognizes, the states Janan recognizes, the observables David recognizes, the observables Janan recognizes, their algebraic structure that seems to many people to be all we should ask of a relation of physical equivalence. So there's pretty good historically entrenched reasons to think that unitarily equivalent Hilbert space theories, Hilbert space representations, are also physically equivalent. That's why I cut off the word. So the Stone-von-Neumann theorem amounts to a reassuring yes answer to the question of whether, in fact, if we follow the recipe, there's only one thing we're going to wind up with. That's the quantum theory attained by Hamiltonian quantization. Okay, so that's why the Stone-von-Neumann theorem is reassuring. But there's also a respect in which the Stone-von-Neumann theorem isn't reassuring. And it's this. It could happen that the classical theories set out to quantize involve infinitely many degrees of freedom. It could happen that the classical theory set out to quantize is a field theory, which assigns a magnitude of some sort, scalar, vector, tensor, to every point of space-time. It contains many points of space-time. It contains many degrees of freedom in this theory. It could be the quantum theory we're trying to build, the quantum theory that lives at the thermodynamic limit of quantum statistical mechanics, which is the limit when you're considering a statistical system as its volume and its number of constituents go to infinity. So again, in the system you're trying to build a quantum theory for has infinitely many degrees of freedom. These are important quantum theories, quantum field theories, the stuff of the Standard Model, of totally venerable physical theory, quantum statistical mechanics, kinetic matter physics is a realization of that. That's why we have iPods. So to get theories like this, we can still follow the Hamiltonian quantization recipe, or a recipe that sets up canonical commutation relations with a target. We can still follow that recipe, but the Stone-von-Neumann theorem, the uniqueness theorem, presupposing as it does that the theories we set out to quantize have only finitely many degrees of freedom, they fail to apply to the quantizations we're after. So if we're setting out to quantize a field theory, it could happen that everybody goes off on the coffee break, comes back with their quantization of the field theory, and they're pairwise physically inequivalent. According to this criterion of physical equivalence, unitary equivalence, that reassured us the quantizations of finite classical theories were reassured and unique. We could all come back with physically distinct quantum field theories. In fact, according to the criterion of physical equivalence, there can be continuously many physically distinct, physically rival quantum field theories that arise by Hamiltonian quantization of classical field theory. Because unitarily inequivalent theories are something physically equivalent. This is pretty abstract. What is the quantization of free boson field if there's continuously many apparently rival contenders? That's why I think it's interesting to raise interpretive questions about these field theories. Okay, so what's the upshot? Well, there's lots of upshots, but here's one. I think that this suggests that often the commitments by which we identify a physical theory fix which physical theory we're talking about. In the quantum case, these often take the form of commitments to a set of commutation relations, canonical commutation relations. They don't finish the job of fixing the content of that theory. Which representation is the right one might be one way to dramatize the open questions. Here are other versions of the open questions. So the canonical anti-commutation relations and canonical commutation relations, they tell you something about what the observables of the theory are. Their observables touch down to one another in the relations specified by the canonical commutation relations. But there's further questions like, what other observables, what other physical magnitudes are there? How you answer this question depends on what account of limit you're going to give. If you decide what the collection of physical magnitudes are, there's a question of what valuations on this collection of physical magnitudes are physically invisible states. That's a real question. What's the appropriate criterion of physical identity for states so understood? That's a further question. What forms, this is a dynamics question, what forms of time development do physical states or magnitudes admit? And these are all interpretive questions. These are all questions, the answering of which tells you a little bit more about how the world could possibly be the way the theory says it. It tells you a little bit more about how the theory organizes possibilities. So there I tell you a little more about what it is to be world of possibilities. And I just tried to suggest by talking about this non-uniqueness of the upshot of Hamiltonian quantization for field theories. These kinds of questions are particularly open for a large and important class of theories that include quantum field theories. You don't even know what the canonical magnitudes are in the sense that there's continuously many candidate representations of the canonical commutation relation. Another claim, commitment to a theory in a form that fosters that theory's capacity to function in physics can require settling answers to at least some of these further questions, some of these content elaborating questions. I can't tell you, go get a representation of these CCRs and you thereby have a fully functioning physical theory. You often have to do a lot more to get it to have traction the way you, and the problems you want to apply it to. Coming back to Fine, coming back to a little more Noah, so does towing the homely line of accepting science on its own terms. In each case, in each circumstance, the content adequate to the scientific aims at hand are reasonable terms for scientific theory to demand. So, in order to do science, we sometimes have to answer some of these content elaborating questions, is what I'm trying to suggest, having indicated that they're open to interesting theories. Once we recognize the burden will fall on us to answer content elaborating questions, we might want to distinguish two strategies for deciding how to do it, deciding what to accept, where we accept science on its own terms. One is to answer the entire imaginable slate of content elaborating questions thoroughly, answer them all, answer them either antecedently to any application of the theory or independent of any application of the theory. The idea being the answer you come up with serves every application of the theory, every application of the theory. Another strategy is to adapt your answers as well as the list of content elaborating questions they're answers to the problem at hand. And these should seem like a familiar sort of pair of strategies. I'm going to say the former strategy is something like the Cyclops realist strategy of interpretation. It's going to call out our theory to be adequate to the challenges it faces by answering the content elaborating questions in one single way. The latter strategy is the localist strategy. And I think the locavore strategy, it's got a methodological advantage. Following it, taking the questions as they come. It has the feature that you could wind up constituting the position sought by the realist and the naturalist. It could turn out, you get the same answer every time. It could turn out there's a single answer that if you go through bite-sized chunks, it turns out you're always chewing on the same thing. So if the realist/naturalist position is tenable, the locavore strategy of interpreting in bite-sized chunks will reveal that, or can reveal that. But it could also be that pursuing the project of interpretation in bite-sized chunks, you find that you're getting a collection of locally generated answers that don't dovetail, don't fit together, mutually contradictory or intentional. And that's the outcome the locavore predicts. Hypothesis she adds on to her stringent methodological recommendation, interpreted bite-sized chunks. Hypothesis is, and you're going to wind up with more than one. You're going to need more than one interpretation to do the set of tricks you want the theory to do. And I close by talking about a few examples that I think lend support to the locavore hypothesis that the questions you ask and the answers you wind up giving to them change from circumstance to circumstance, so that there isn't a single single Cyclops interpretation that is the stuff of realism or naturalism. Let's start. Maybe not entirely disingenuous, the chosen theoretical virtue of fertility, capacity to serve as a springboard for future scientific theorizing. So that's a virtue. Good theories point you toward their successors, give you direction. Think about how a theory, quantum field theory on curved space-time, exhibits this virtue in the context of probing towards a future physics that includes quantum gravity. So here's one way quantum field theory on curved space-time serves that virtue. So there are Einstein's field equations, a couple differential equations. The guy on the left-hand side is a guy who describes space-time curvature. The guy on the right-hand side describes These are matter, energy, and space-time. Those are the real first. Groping towards quantum gravity. You might do something called semi-classical quantum gravity. And what you do when you do that is you imagine space-time, you imagine a state of a quantum field on space-time. And you use this quantum field state on space-time to attribute stress energy to the guy on the right-hand side of the field equations and expectation value. You're sort of inserting a quantum element into the classical field equations. And you're doing it by imagining space-time in a quantum field state and using that quantum field state to describe stress energy distribution. Semi-classical quantum gravity. That's your project. A question you should ask if that's your project is which states of the quantum field are physical? Which states can you put there such that the expectation value is well defined? If you have states in your theory that disappoint, frustrate the calculation of the expectation value of stress energy, you have states in your theory that frustrate, disappoint the whole semi-classical quantum gravity. It makes sense to think about. And it turns out, there's something really nice about this, that there's a way to characterize states of the quantum field that enable the stress energy tensor to receive an expectation value, and thereby enable the project of semi-classical quantum gravity. And the characterization has to do with singularity structure of states, the fact that the fields at different points approach each other. In a word, the criterion that states have to pass in order to effectively assign an expectation value to the stress energy tensor is something called Hadamard criteria. So, what you're doing when you're saying, as far as I'm concerned, the state of the quantum field in curved space-time has to satisfy the Hadamard condition to be physical, because otherwise it doesn't cooperate in the project of semi-classical quantum gravity, and that's an important project if you're interested in going forward with a project, the cooperation of which renders quantum field theory in curved space-time fertile. What you're doing when you're giving the answer Hadamard states or physical states is you're interpreting quantum field theory in curved space-time. You're framing a content-elaborated question and giving an answer to it. A content-elaborated question's answer is not dictated by the quantization and founding and representation of the canonical relation. Yes, but here's the thing. Fostering the pursuit of semi-classical quantum gravity isn't the only way quantum field theory in curved space-time helps direct us towards future theories of quantum gravity. It isn't the only way quantum field theory in curved space-time is fertile. There's another way. Hawking effect, black hole evaporation. It turns out black holes aren't really black, they radiate, they spit out radiation. Spit out radiation, lose mass, disappear, it's very upsetting. Once they disappear, there's the sea irradiation, where the thermal signature of radiation tells you about initial properties of the black hole. This is all theoretical prediction. But the theoretical prediction that plays a very interesting role in the tussling over how to pursue quantum gravity. There isn't many empirical constraints on quantum gravity. The reproducing the phenomenology of Hawking radiation, being able to describe the thermal spectrum so that it's related in the right way to the initial mass of the evaporating black hole, kind of serves people who fight over quantum gravity as a semi-empirical constraint. So they take it to be a virtue of string theory or loop quantum gravity that kind of delivers the description of Hawking radiation Hawking made. Okay. There's a Hawking effect, like a constraint on Fletcher in theories of quantum gravity. And back to the interpretive project, we want to interpret quantum field theory in curved space-time in such a way that it sustains projects in physics development, particularly the development of quantum gravity. There's a few features of Hawking radiation, in particular, if you're an observer outside a black hole that's evaporated, what your world looks like. There's features of Hawking radiation as modeled by quantum field theory in curved space-time that are best modeled by non-Hadamard states. That is, they're best modeled by states that don't cooperate in the project of semi-classical quantum gravity. So, this is way too quick, but I'm trying to suggest. If you care about fertility, think that's a virtue that's going to drive an interpretive agenda. And following that interpretive agenda in the context of semi-classical quantum gravity, you're going to identify a content elaborated question, what states are physical, or give one answer to it, Hadamard states.